Yeah, hello everyone. Uh, this is solid state video number 4. In the previous video, we discussed the different types of unit cells, and in this video, let us take the basic crystal systems and Bravais lattices. Particularly for mains kind of examination, this particular classification is very much important. Already in the last video, we discussed that there are 6 different parameters uh, what do we call to describe unit cells. Their axial lengths and axial angles. Axial lengths are ABC. Axial angles are alpha, beta, and gamma. Now, so based on the magnitudes of axial lengths and axial angles, all crystal systems are classified into 7 types. Those 7 crystal systems are said to be basic crystal systems. So based on the magnitude of axial lengths and axial angles, all crystal systems are classified into 7 types. And these 7 crystal systems are said to be basic crystal systems. And in that basic crystal system, what type of unit cells are present? What type of unit cells are found? What type of unit cells are possible? Based on that, these basic crystal systems are further classified, and ultimately we'll be getting Bravais lattices. We are going to get 14 Bravais lattices. So basic crystal systems based on the type of unit cells present in this. Each basic crystal system is further classified. Altogether, finally, we are getting 14, and all those 14 lattices are called Bravais lattices. And here, particularly for mains examination, this table is very, 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 very important. And here, the name of the crystal system, the possible unit cells present in that system, and in this system, what are the axial lengths, what are the axial angles, what kind of examples. So every column in this table is very important, particularly for the mains examination, I told you. So the first system, see, this is basic crystal system. Crystal system means basic crystal system, that is a cubic crystal system. And here the axial lengths are A, B, C, all are equal. Axial angles alpha, beta, gamma, all are equal. And in case of this cubic crystal system, 3 types of unit cells are found. Actually, we have 4 types of unit cells in general, but the cubic crystal systems have 3 types of unit cells. 3 types of unit cells were identified in case of a cubic crystal systems. So what are the 3 types? Primitive, body-centered, face-centered. And this is a basic crystal system. And the Bravais lattices in this basic crystal system are 3. What are the 3 now? What do we call? Primitive cubic or simple cubic, you can say. No problem. Simple cubic, body-centered cubic, face-centered cubic. So cubic system, that is a basic crystal system. And if you add the type of unit cell present in that, now it is called Bravais lattices. So 3 Bravais lattices, actually they are a simple cubic, body-centered cubic, face-centered cubic. How to define a cubic crystal system means by taking these parameters. What are the examples means? So here, whatever the examples we are going to study in this chapter, all of them come under cubic crystal systems, because for JE we have cubic crystal systems. And the second type of basic crystal system is a tetragonal. How to define a tetragonal basic crystal system? A is equal to B, but B is not equal to C. Alpha is equal to beta is equal to gamma, that is equal to 90. And in case of tetragonal crystal system, 2 types of unit cells were found. One is primitive, another one is body-centered. So one more point I'm adding, in all 7 basic crystal system, there is primitive unit cell for sure. Every basic crystal system has primitive unit cell or basic unit cell. Along with that, there is also body-centered unit cells. So here Bravais lattices are 2 in case of tetragonal. One is a simple tetragonal, another one is a body-centered tetragonal. What are the examples means? These examples are 100% sufficient because these examples are mentioned in NCERT textbook. And the next one is orthorhombic. Orthorhombic crystal system, basic crystal system. How to define? A is not equal to B is not equal to C, but alpha, beta, gamma all are equal, and that is equal to 90. And in this, all the 4 types of unit cells were found. Simple orthorhombic, body-centered orthorhombic, face-centered orthorhombic, end-centered orthorhombic. Here there is a possibility for asking a question. Which of the following basic crystal system has all 4 types of unit cells? Undoubtedly, orthorhombic. And basic crystal system has all 4 types of unit cells. Which of the following condition is true? They may give different options, but which condition is true? A is not equal to B is not equal to C, but alpha is equal to beta is equal to gamma, and all these are equal to 90, and these are the examples. Next, hexagonal crystal system. Hexagonal, basic crystal system is hexagonal, and only one type of unit cell was found, that is simple hexagonal or primitive hexagonal. This is Bravais lattices, Bravais lattice. And how to define this? A is equal to B but not equal to C, and alpha, beta are equal 90, and gamma is equal to 120. And these are the examples: graphite, zinc oxide, cadmium sulfide. And here also there is one possibility, and here hexagonal crystal system has only one type of unit cell, primitive. Of course, some more examples we have of the same category. So trigonal or rhombohedral. Trigonal or rhombohedral. Even in this, there is only simple unit cell or primitive unit cell. And how to define? A is equal to B is equal to C, and alpha is equal to beta is equal to gamma, but these are not equal to 90. If any basic crystal system is having these kind of dimensions, that is called trigonal or rhombohedral, and these are the examples. Only one type of unit cell was found, that is simple. And the next one is a monoclinic. In case of monoclinic basic crystal system, how to define? A, B, C, these are not equal. A is not equal to B, not equal to C, but alpha is equal to gamma, which is equal to 90, but beta is not equal to 90. 2 types of unit cells were found in this. One is the primitive, another one is end-centered. And these are the examples. And the last one, that is a triclinic. Triclinic. So a crystal system is said to be triclinic if the dimensions are like this. A is not equal to B, is not equal to C. Alpha is not equal to beta, not equal to gamma, that is not equal to 90. And only one type of unit cell is found. And these are the examples. And the most important thing, no 2 axial lengths are same, no 2 axial angles are same. So we can say, based on these dimensions, this is the least symmetric solid, least symmetric basic crystal system, that is a triclinic. Most symmetric crystal system is what do we call a cubic. And if you count 1, 2, 3 here, 4, 5 plus 4, 9, 10, 11, 12, 13, and 14. So this column will give you Bravais lattices. This column is giving you, what do we call, basic crystal system, axial lengths, axial angles, and examples. 100% very much important for mains kind of examination. So this is about the basic crystal systems and the Bravais lattices. And in our syllabus for JEE, we have cubic crystal systems along with that hexagonal. But the cubic crystal systems extensively we have to study. Extensively we have to study. So first let us understand the internal structure of a cubic crystals. In order to study the internal structure of cubic crystals, there are 3 types of unit cells I have just discussed. One is a simple cube, body-centered cube, face-centered cube. So we have to study where the particles are present and how many effective atoms are present, what is the density, what are the voids, what are the different types of voids. We have to study these cubic crystal systems completely, but we need some basic idea about the 3 types of cubic unit cells. Now, so this is, for example, these kind of example diagrams will help you see. This is the cubic crystal system. A is equal to B, B is equal to C. So here all 3 axial lengths are same. and all three axial angles are same, and this is a tetragonal. And here, like this, we can understand, we can see what is this basic crystal system and what are the dimensions. And this is a triclinic, for example, the least symmetric one. So no two axial lengths are same, no two axial angles are same. So here, this is about basic crystal systems and Bravais lattices. And the first one, the most important one, calculation of number of atoms in unit cell. Already in the previous video, we discussed what is a simple unit cell, what is a body-centered unit cell, what is a face-centered unit cell. Simple unit cell means the particles are present only at the corners, and the body-centered unit cells means the particles are present at the corners and the body center. And in case of face-centered unit cells, the particles are present at all face centers and all corners. But end-centered unit cells are not found in cubic crystal system. That is clear. Cubic crystal systems are only three: simple cube, body-centered cube, face-centered cube. But the most important calculation we have to do, what exactly we are trying to do, effectively how many atoms are present in a cubic unit cell. So what does it mean? Effectively, what does it mean? See, already told you during the formation of crystal lattice, all unit cells are arranged systematically, and whenever unit cells are arranged, so here in all directions, some of the atoms, some of the constituent particles are shared by more than one unit cell. And what is this sharing? How to understand this sharing? And how to calculate effective number of atoms after sharing. Effectively how many atoms are present, effectively how many atoms are present, we have to calculate. But here let me explain with the help of all diagrams. So here listen carefully, here it will be very much useful. First, let us try to define a body centered atom. Body centered atom. So what is the nature of this body-centered atom? How many body centers are present and what is the nature? Very clear, body-centered atom, if you observe, the particle is present at the center of the unit cell. This is not in contact with other unit cells. That means left side, right side, above, below, back, front, this unit cell is surrounded by other unit cells in all other directions, but this body-centered atom is not in contact with the other unit cells. So other unit cells are not sharing this. Other unit cells are not sharing this because it is lying completely inside. So only one body center, obviously body center is only one, and this atom belongs to only one unit cell. This atom belongs to only one unit cell because this is not in contact with other unit cells, and obviously the contribution of that atom is one. Contribution of that particular atom to this unit cell is one. This atom is belonging to one unit cell. Obviously how much it is contributing means only one, and effectively how many atoms means one, and this calculation will do. First, let us try to define the various atoms. See for example, face centered atom we are talking about, the particle which is present at the center of the face. You see, this is one unit cell, this is another unit cell, and between these two unit cell there is a face which is common, and the particle is sitting at the center of this face. When the particle is sitting at the center of this face, so what will happen? This unit cell will share, this unit cell will also share that particle. So both the unit cells have right on that particle. So this unit cell is sharing, this unit cell is also sharing, and this particle is equally shared by two unit cells. But practically we are not cutting. Please understand, we are not cutting. That is not possible. Effectively how many atoms are present in one unit cell, that is our calculation. And when it is present at the face center, this is equally shared by two unit cells. As a result, on average, this is getting 1 by 2. This is also getting 1 by 2. So I need 2 points now. Face center atom or face centered particle is shared by 2 unit cells. 2 unit cells. What is the contribution of a face centered atom? 1 by 2. That means this atom or this particle is contributing 1 by 2 to left side unit cell, 1 by 2 to right side unit cell, because it is shared by 2 unit cells. That is the situation of a face-centered atom in cubic unit cells, right? Now let us take edge-centered particles. If the particle is present at the center of the edge, what will be its environment? What will be its situation? And how many unit cells are sharing that? And what will be the contribution of that atom to each unit cell? That is our discussion. And you can see this is one edge. Any edge you can take in this picture. The situation I'm explaining by taking one example, and the same can be applied to all edge-centered atoms. See, for example, this is one edge. At the center of the edge, there is a particle, and if you see in this diagram, this particular edge-centered atom or particle is shared by 4 unit cells. You can see that is shared by 4 unit cells. What are the 4 unit cells? 1, that is 2, and this is 3, and this is 4. Bottom unit cells 2, top unit cells 2. Bottom left, bottom right, top left, top right. See, this ultimately this edge-centered atom is equally shared by 4 unit cells. I need only the 2 numbers. Edge-centered atom. It is shared by how many unit cells? 4. How? Like this. Now, one edge-centered atom is shared by 4 unit cells. What does it mean? Each unit cell will get how much? 1 by 4. Contribution of constant particle, contribution of edge-centered atom to each unit cell is how much? 1 by 4. In fact, these things only have written, and here corner particles. Now, what is the situation of corner particle? What is the situation of corner particle? See, for example, if a particle is present at the corner, and here bottom there are 4 unit cells, top also there are 4 unit cells. In this diagram, if you see, bottom unit cells 4, top unit cells 4. So here bottom left front side, and this is right side, and this is back side. Let me write the numbers. This is the first unit cell, this is the second unit cell, and this is the third unit cell back side, and the back left, and here top unit cells now I'm defining. So left, so that is a top left, so here that is a top right, so here this is the 6th one, and this is back side 7th one, and here there is 8th one. That means when a particle is present at the corner of a cubic unit cell, that is equally shared by 8 unit cells. So corner atom is always equally shared by 8 unit cells. So what is the contribution of corner atom? 1 by 8. It contributes 1 by 8 to each unit cell. You can see here, practically already told you it is not possible to cut like this. But what I'm trying to convey, effectively, if you want to calculate the number of constant particles, you need to know effectively how many atoms from face center, body center, edge center, and corner. So here, totally, here this corner particle is equally shared by 8 unit cells, and each unit cell is getting how much? 1 by 8. So this is the situation of 4 types of particles in cubic unit cells. Body center particle situation, it is not shared by other unit cells. It belongs to only one unit cell. It belongs to only one unit cell. Face-centered atom, this face-centered atom is shared by 2 unit cells. So the contribution is 1 by 2. Contribution is 1 by 2. And the edge-centered atom is shared by 4 unit cells, and the contribution is 1 by 4. Now, corner atom, if you see, it is equally shared by 8 unit cells, and the contribution is 1 by 8. Now we need to find number of atoms in primitive cube, body centered cube, face centered cube. So that will be the end of this video. So easily, whatever the things we understood based on that, easily we can calculate. So first let us take a primitive unit cell, primitive cubic. Okay, primitive cubic. So first thing, primitive cubic means basically cubic unit cell. A is equal to B is equal to C, alpha is equal to beta is equal to gamma, which is equal to 90. And the primitive unit cell means the particles are present only at the corners. It has atoms only at the corners. Effectively, how many atoms? Effectively, how many atoms in one unit cell? Effectively, how many atoms? See, this is the unit cell view. This is the unit cell view, and this is atoms contact view, and this is the slice view. Generally, to explain, we write like this, but there is a contact between the atoms. These are what do we call? These are the constant particles in solid state. So definitely the particles are arranged very closely. So this is the unit cell view. So this is atoms contact view, and this is the slice view. We can see when you say primitive cubic unit cell, the particles are present only at the corners. But I need effective number of atoms. All the 8 atoms belonging to different unit cells. This is belonging to 8 unit cells. This is belonging to 8 unit cells. This is also belonging to 8 unit cells. Just now I told you. And a corner atom, each corner atom contributes how much? 1 by 8. Each corner atom contributes 1 by 8 to each unit cell. Like that, how many corners? 8. That means this unit cell is getting 8 1 by 8s. This unit cell is getting 8 1 by 8s. It is getting 1 by 8 from each corner. Altogether, it becomes 8 1 by 8. 8 1 by 8 means that is equal to 1. Effectively, there is only one atom. 1 by 8, 1 by 8, like that. 8 1 by 8, that is equal to 1. You can see this is the atoms contact view, and this is the slice view. Because the atoms, you can see they are divided, because some fraction is going into other unit cells. This is about so what is this is actually called a rank of the unit cell. This is called rank. Rank of simple cubic unit cell is 1. Now let us take a number of atoms in BCC unit cells. Atoms means very clear, we are finding rank of the unit cell, which is nothing but effective number of atoms. Effective number of atoms. BCC unit cell means, what is the full form of this abbreviation? Body centered cubic. Body centered cubic. But in general, I suggest the students, like you remember like this. The particles are present at body center, and this is C corner, but actual full form is body centered cubic. So this is indicating what do we call a basic crystal system, and this is indicating type of unit cell. And altogether, you can easily remember the particles are present at the body center and corner. Body centers are how many? 1. What is the contribution of body center? 1. Because it is not shared by other unit cells. So it is getting 1 from body center, and 1 by 8 from 8 corners. See, this is the situation. A BCC unit cell, if you observe, the particle is present at a body center, and also the particles are present at corners. The same particle, right? See, this is particle, and this is also the same particle. If it is atom A, these are also atoms A, not different atoms. Please understand clearly. Body-centered cubic unit cell means the same kind of atoms are present at the body center and all 8 corners. And this is atoms contact view. And the body center is belonging to one unit cell completely. It is not shared by other unit cells, but 8 corners, and each corner is contributing 1 by 8. And from 8 corners, it is getting 8 1 by 8s. That is equal to 1. So effectively, how many atoms are present? 2 atoms, and the rank of the unit cell is 2. Rank of the unit cell, BCC unit cell, has 2 atoms of the element, what do we call effectively, and this is the slice view. You can see the full atom is sitting at the body center. And the last one, that is FCC unit cell. Actually, what is the full form? What is the full form of this abbreviation? Face-centered cubic. But I suggest, if the students, they may forget like that, I suggest, so the particles are present at face centers and corners. but the abbreviation, full form of this abbreviation is face-centered cubic lattice, right? And all face centers, how many face centers? 6. You first see the diagram. You first see the diagram. This is FCC unit cell. Already told you yesterday, left face, right face, what do we call back face, front face, top face, bottom face, and corners. And this is unit cell view. This is atoms contact view. You can see this is one face. So this is one face actually. So if you carefully observe, there are totally 6 faces, and here this is one face, and this is a second face, and here this is the third face like this, and the back side, and here back side one, and the bottom. So the particles are present at all face centers and all corners, right? And how many face centers? 6. What is the contribution of face centered atom? 1. Contribution 1 by 2. Face centered atom is shared by how many unit cells? 2. Each face center is contributing 1 by 2. 6 face centers are totally giving 3 atoms effectively, because 6 1 by 2s are coming from all face centers, and 8 1 by 8s are coming from corner. As a result, it becomes 1 corner atom effectively, and altogether if you calculate, this is 4. And finally, what we can say, the rank of FCC unit cell is 4. Rank of BCC unit cell is 2. The rank of simple cubic unit cell is 1. So this is about a calculation of number of effective number of atoms in each cubic unit cell. And with this, let me conclude. And this is solid state part 4. In the continuation video, so we'll be talking about the different types of parameters like effective, Z effective, atomic radius, coordination number. Those things we'll be discussing in the next video. And thank you very much.